We're going to look now at conducting a hypothesis test when we know the population standard deviation. Creating the confidence interval for a sample mean required three pieces of information from the sample. It required the sample mean, the standard deviation, which could either come from a population standard deviation or a sample standard deviation, and the number of observations. When the standard deviation is known, only one population parameter is estimated from the sample, and that is mu, from the sample mean. The confidence interval in that case was then x bar plus or minus some z score or z multiple times sigma, which is the population standard deviation, over the square root of n. Recall that the formula says that when alpha was 0.05, the confidence level was 1 minus alpha. So therefore, it was 95%. And thus 95% of all sample means reside within that confidence interval. Thus, we infer that there's a 95% chance that the population mean resides in that confidence interval. Well, that's not the exact definition. So what we're going to do is we're going to conduct what we call a z-test. If a sample mean and a population mean were identical, then the difference between the two would be 0. Now, we saw this from a z-score originally, that if you had your x bar minus mu, the numerator was 0. We're going to do something very similar. So recall that z statistic for the sampling distribution was z equals x bar minus mu over sigma divided by the square root of n. If the fraction is between negative 1.96 and 1.96, then the population mean and sample mean are within two standard deviations of each other, and the population mean will be statistically equivalent to the sample. Now, if the sample mean were identical, then the difference between the two would be 0. In this case, the numerator of the fraction is close to 0, making the z statistic close to 0. So calculating the z value of the difference between x and mu allows for the probability that the two are statistically the same or different. This is known as comparing the sample mean to the population mean. Let's assume that we have a sample mean of 50 and a population mean of 55. The population standard deviation is 7.2, and the number of observations is 100. Using that information, we can now compute a z-value. So we have 50 minus 55 divided by 5 over the square root of 100. When we put that all together, we end up with negative 5 over 0.5, which gives us negative 10. Well, what does that mean? Well, it means that we can now use that and determine that z-value in that standard normal distribution. So here's our curve. So the z statistic was computed as negative 10. Looking at the graph, negative 10 would appear way beyond to the left, the 95% middle interval to the left, meaning that there is a strong difference between the sample mean and the population mean. You can see that we've got negative 1 and negative 2, which is, again, my scores, right? That negative 2 for that z-score is going to be my 95%. Once it falls way beyond that to the left or way beyond that to the right, we're going to have a difference. So how do we compute the p-value? So we saw that it's all the way in the tail, so that's a sign that there's going to be a difference. But what we're going to do is we're going to compute the p-value. Now, while there are tables in statistics books, it's going to be easier to use statistical software. When I was doing statistics, I had to use the tables in the back of the books and so forth, but we're going to be a little bit more advanced and we're going to use Excel. Now recall that if we had a z-score, we could calculate the probability to the left. And we did that with this norm.s.dist. So if we put norm.s.dist with a negative 10 and a true for cumulative distribution, we would get a very, very small number, like 0. And so this means that the probability of this z-score is very close to 0. So now we can compare that statistic to the p-value. So once the p-value is obtained, which we did which is a 0, we compare it to the alpha value. And this will depend on the type of test, whether it's one tail or two tail. If alpha is 0.05 and the test is two tails, such as the one above, we will divide the value by 2 because, again, you're going to have what's only in the tails. If it's a one-tail test, you leave the alpha value as is. Once we do that, we're going to compare that p-value now to either alpha or alpha over 2. If the p-value is smaller, then the null hypothesis is rejected. Otherwise, it is not rejected. Let's remember why we're cutting that alpha value in half. If the rejection region is in the tails and the focus is on the middle 95%, the tails will have an area of 5% in total, which means 2.5% in each area. This area represents the rejection region. Thus, if the p-value is less than this area, then H0 will be rejected. In a one-tail test, we do not need to cut it in half. So if alpha is 0.05, then the desired region in the tail is the full 5% by itself. This area below, the blue or the red, is the entire rejection region on the left or on the right, depending on if you're looking at the one tail on the right side or the one tail on the left side. Even though we've talked about it, it might be easier to review in a graph. So first, is it a two-tail test? Yes, we'll use alpha over 2. If no, we'll just use alpha. Now we'll actually conduct the test. Once we've computed the p-value, is the p-value less than or equal to alpha, or alpha over 2, depending on which way we're going to do it? If the answer is yes, we reject H0. If the answer is no, we do not reject H0, or the null hypothesis. The bottom right here kind of does it in a little bit of code for someone who's more computer program oriented. If the p-value is less than alpha or alpha over 2, reject H0. Else, do not reject H0. So looking at the previous sample, the hypothesis test is more formally constructed on the left here. We have our x bar equals 50, our sigma equals 5, n equals 100, mu equals 55. We said H0 is x bar equals 55, HA is x bar not equal to 55. It's clear it's a two-tailed test, so the alpha value is going to be divided by 2, 0.025. Then if the p-value is less than our significance level of 0.025, we will reject H0. Since we had computed in Excel that this was negative 10, the probability was 0 as the p-value, we then can basically reject H0, and we can say that we reject the null hypothesis, or H0, and thus we have evidence to support that the sample mean is not equal to the population mean. Let's look back a little bit at when we did it with the confidence interval. So using the exact same numbers, if a confidence interval was computed, we'd have 50 plus 1.96 times sigma over the square root of n, which equals 50 plus 1.96 times 5 over the square root of 100. This gives us 50 plus 1.96 times 0.5. The confidence interval was 49.02 to 50.98. And it is clear that the population mean of 55 from the previous slides would not sit in this confidence interval, meaning that the sample must have come from a different population. Using a graphical representation of what's actually happening, assume the red curve represents a sample, with the red stripe as its confidence interval around the sample mean. The blue curve represents the population, and the center line is the population mean. Now note, that's going to be a lot smaller because there is no confidence interval around a population mean. It's only around the sample. In the case that the population mean doesn't fall within the sample confidence interval, it means that the sample must have come from a different population. It has an entirely different curve. It's shifted. It may have, something look a little bit differently, but it is definitely coming from a different population. Consider a population with vitamin D levels around 30, and a sample of people are given a pill. The population mean lies outside of that sample confidence interval. It would mean that those two groups of people are completely different, and it must be because of the pill that they were given. On the other hand, if the population mean lies within the confidence interval, then as the graph shows, they're very close to each other. And the only difference you really see would be due to nothing more than just some chance. It is this reason why the concept of a sample being from the same population or not is how analysts can tell whether or not something is the same or different. A closer look at the p-value. Since the p-value is a probability, the number will always be between 0 and 1. It is the interpretation of a type 1 error. That is, rejecting the null hypothesis when it shouldn't have been rejected. If the p-value is 0.001, for example, then the probability of a type 1 error is 0.1%. The easiest way to interpret this would be to compare the p-value to the significance level. In order to reject the null hypothesis, the p-value must be less than the significance value of alpha, or alpha over 2 if that's what you're working with in a two-tailed test. For example, if you have a p-value of 0.03 and a significance level of 0.05, you can then reject the null hypothesis. Now, in practice, consider the p-value as a measure of risk along with your significance level. Assume you were looking to place a bet on a blackjack table and you want to bet $1,000. What if you had a machine that said, you should bet $1,000 because you have a 95% chance of getting an ace, which would double your money? In other words, there's a 5% chance that it's wrong. Would you place the bet? What if the machine said there's only a 6% chance that it's wrong? What about 7 or 10 or 15? Would you still place the bet? When looking at these types of decisions, your significance level should be related to the outcome and the level of tolerance you have for the decision being wrong. This could be based on ROI or some other measures or anything else that the person who's the recipient of the analysis intends to do with the information. In general, academic studies fix the significance level at 0.05, with 0.10 occasionally in some psychology and behavioral research. The 0.05 is really not a magical number. It's simply a number that has been used over the years in academic literature as an accepted standard. And in fact, there have been some papers written in statistical journals that talk about the p-value should never have been used in this manner. But for the purposes of this course, you can consider doing 0.05 if no other significance level has been stated. Let's look at the sample of human body temperature again. So consider a sample set of patients entering a hospital. The 80 patients have a sample mean temperature of 98.71. The doctors want to see if this sample is different from the population mean. And we know that the population mean of the human body temperature is 98.6 with a population standard deviation of 0.62. So we've set everything up on the left where n is equal to 80, sigma is 0.62, mu is 98.6, and our sample mean is 98.71. We set up our null and our alternative hypothesis. Again, x bar is equal to 98.6. X bar is not equal to 98.6. Remember, our z formula is x bar minus mu over sigma divided by the square root of n. We plug in our numbers over here, and we end up with a z-value of 1.59. We'll take that 1.59 and we'll put it into the norm.s.dist. Since the sample mean is greater than the population mean, we're going to subtract the value of 1 to get that right tail probability, and we get a result of 0.056. Because the null hypothesis is just equal, this is a two-tailed test, so the alpha value needs to be halved. Therefore, alpha is 0.025. This will be the value to compare against. If p is less than 0.025, then we're going to reject H0, else we do not reject H0. Based on the rule for rejection, the null hypothesis is not rejected, and therefore we do not have evidence that the sample is different from the population, or we have evidence to support that the sample is the same as the population. Both would be acceptable because we're saying we have evidence to support or we do not have evidence for the first case. Let's assume that the z-value was negative. So in this case, we have an x bar of 98.49 instead of the value that we had before, which was 98.71. Because our z-value is negative, we're looking for that tail on the left side because it's norm.s.dist negative 1.59. So in this case, because it's negative, just provide the straight value for the left tail, no need to subtract 1. The rule is then applied as before. We will take p less than 0.025, reject H0. If it's otherwise, we do not reject H0. Based on the rule, the null hypothesis again is not rejected, and therefore we do not have evidence that the sample is different from the population. We say left side and right side even though it's a two-tailed test, but that's only to deal with the sign and whether or not in Excel we're using 1 minus or not. Now, there is a way to do it either side if we simply just use the absolute value of that number. Whether it was negative or positive, you would then always do 1 minus here. So you can see here in Excel, we did 1 minus norm s.dist ABS, absolute value of negative 1.59. And if you did absolute value of a positive number, it would give you the same thing. And your result is the same. Now, with a one-tailed test, the focus is on whether the sample mean is above or below the population mean. The hypothesis test is generally set up the same way. So we're going to have a different example here. Assume a marketing manager wishes to determine if revenue rose from a marketing campaign. The historical average sales is 47.89, with a general standard deviation of 3.5. After taking a sample of 100 receipts, the sample average is 48.50. The setup of our hypothesis would therefore be X bar is 48.5, sigma is 3.5, n is equal to 100, and mu is 47.89. Our null hypothesis is X bar is less than or equal to 47.89, and our alternative hypothesis is that X bar is greater than 47.89. So this is a one-tailed test. We'll now plug in all the numbers here, and we've set everything up on the left. We have our alpha value of 0.05. We've set up our hypothesis tests here. We're using our Z formula. And we've computed the Z statistic here, plugging in all the numbers, and get 1.74. We'll do 1 minus norm.s.dist, 1.74, again, because it's on the positive side. And we're looking for the right tail. This would give us a 0.041 p-value. Since the p-value is less than 0.05, we will reject the null hypothesis. And therefore, we have evidence that the sample mean, 48.50, is statistically greater than the expected value of 47.89. And therefore, the marketing campaign seems to have worked. Now, what if the marketing manager wanted to be 98% certain and not 95% certain? The alpha value would then just need to be changed to 0.02. No calculations really need to change, only the analysis. Because now instead of p being less than 0.05 for our rejection factor, we're going to do p less than 0.02. Since 0.041 is not less than 0.02, the null hypothesis is not rejected, and therefore we have no evidence to support the notion that the sample is different from the expected mean of 47.89 at a 98% confidence level. Now, what if we were looking at this from the other side? What if a mistake was made and instead of looking at the right side, the value calculated by norm.s was not subtracted from 1? Then the analysis would be looking at the area of the curve to the left of that value. So we have the 1.74. But because we didn't do the 1 minus, it's this entire blue region. And that entire blue region area would be 0.959. And we would clearly reject the null hypothesis because of 0.959, regardless of whether it was 0.05 or 0.02 alpha. So here's a quick summary that we can develop for the hypothesis test when the population standard deviation is known. Our hypothesis for the left side is X bar greater than or equal to mu. Alternative is X bar is less than or equal to mu. We compute the Z statistic from X bar minus mu over the sigma divided by the square root of n. And our rejection is if the p-value is less than alpha, reject H0. Alternatively, we could look at the z-scores using the notion of what's called a z-critical value. So in the case that we were looking at before, that would be the 1.96. Alternatively, we could look at what's called a z-critical value. The z-critical value is going to be based on the value that we're looking at, either 1.96 or negative 1.96. So if the z-value on the left side test was less than that z-critical, which would have been negative 1.96, then we would reject H0 in that case. On the right side upper tail, we do everything pretty much the same, except we're just inverting some of the signs. Our X bar less than or equal to mu for the null hypothesis, X bar greater than mu for the alternative hypothesis. And our Z calculation is the same. And if the p-value is less than or equal to alpha, we reject the null hypothesis. And in the case of the z-score, this time it's a little bit different because if z was greater than the z-critical value, we would reject H0. In this case, the Z critical value would be 1.96, so Z would have to be greater than that. In the two-tailed test, again, we have equals and not equals for our null and alternative hypothesis. Our Z compute is the same. If p-value is less than or equal to alpha divided by 2, we will reject the null hypothesis.